Autonomous Vehicle Science Lecture Series, number 0. Announcement, from MotionLab. A novel motion creation method for autonomous vehicles, AVs. This novel motion creation method MathMind, or MM, possesses the following features and advantages. This method is vehicle hardware independent and sensor independent. 4 mathematical theories formalized and optimized the method. This method creates the most accurate motion for AVs, and makes AVs the safest and most trustworthy. Based on these foundational mathematical theories, this method will never be surpassed. We also developed the most advanced technology for future EVs, Omega-Mode motions, human-made motions, and motion reproduction. Vehicle motion creation. 1. The Omega-Mode. Motion creation is the most essential subtask in an autonomous vehicle, AV. There are 2 motion modes for AV motion creation, the Omega-Mode and Curvature-Mode. 1. The Omega-Mode. In this mode, the 2 variables, omega, v, equals, rotation velocity, translation velocity, are the output of the motion creation subtask, which controls the vehicle hardware. The input to the subtask are omega, t, and v, t. Lecture MM8 Omega Motion tells more detail. An automobile driven by an internal combustion engine cannot function in the Omega mode, but an EV can. In the future, more and more AVs will be EVs. They might use motions in the Omega mode because they have a significant advantage that Omega motions can demonstrate flexible motion in a limited space. Vehicles motion creation. 2. The Curvature mode. In this mode, the 2 variables, kappa, v, equals, path curvature, translation velocity, are the output of the motion creation task that control the vehicle hardware. A human driver controls her car in this way, controlling path curvature, kappa, by the wheel and translation velocity, v, by the pedal, brake. MotionLab invented 5 geometric motions, GMs, for this mode. 1. Direction-Tracking GM. 2. Line-Tracking GM. 3. Circle-Tracking GM. 4. Park Geometric Motion. 5. Curvature-Defined GM. Motion creation subtask is sensor, vehicle hardware independent. The most significant advantage of geometric motions, GMs, is that they are sensor independent and vehicle hardware independent. Because the input and output to and from a vehicle in the Omega mode are kappa and v, which are geometrical, physical entity. The input to a GM is a small amount of geometrical data. The output from a GM is kappa, v, equals, path curvature, translation velocity, that a geometrical, physical entity. The function of a GM is to convert geometric input to kappa, v, that a geometrical, physical entity. Therefore, the input, output, and task of a GM are sensor, vehicle independent as well. We use the following 4 unpublished mathematical theories to create and optimize motion creation capacity. Namely, we follow deductive approaches rather than inductive approaches the AV industry mainly relies on. No AVs for on-street driving testing is necessary. These 4 unpublished mathematical theories are our rock-solid foundation. The following 4 unpublished mathematical theories invented the 5 types of geometric motions mentioned above. The 2D transformation theory. This theory provides arithmetic tools to deal with a 2D rigid body vehicle's static positioning and motion. This is a non-abelian group with a composition operation and an identity element E. The theory of curves. This theory gives us symmetric arches, quantitative evaluation path complexity cost and driving skills, and other methods. The homogeneous differential equation theory. This theory solves the nonlinear differential equations for direction tracking, line tracking and circle tracking GMs. The principles of vehicle motion. This theory deals with omnidirectional vehicles, curvature motion mode versus omega motion mode, and other motions. MathMind technology will never be surpassed. Every mathematical theory has a long life, like linear algebra, topology, and number theory. Likewise, each of the 4 mathematical theories mentioned earlier has a long life. Therefore, all the facts presented in this lecture series will never be obsolete or replaced by other theories. MM-equipped autonomous vehicles will enjoy this stability. 10 lecture series fully describes MathMind technology. Because MathMind is a complex ecosystem and we explain the entire system in these 10 lecture series. MM0 Announcement, MM1 Direction, describes direction-tracking motions GMA number 1. MM2 Line, describes line-tracking motions GMA number 2. MM3 Circle, describes circle-tracking motions GMA number 3. MM4 Park, describes park motions GMA number 4. MM5 Curvature, describes curvature-defined motions GMA number 5. MM6 Safest Vehicle, MM7 Motion Abstraction, MM8 Omega-Mode Motion, and MM9 Man-Made Motion. Hypotheses K1 and K2 prove soundness and completeness of GMs. MotionLab claims hypotheses K1 and K2 as follows. Hypothesis K1: the 5 GMs are necessary and sufficient to create motion for AVs. Hypothesis K2: for any purpose, in any situation, there exists one and only one GM that appropriately handles the situation. We have experienced no counterexample against these hypotheses. These hypotheses prove the soundness and completeness of the set of GMs. A MathMind vehicle acquires trust from people. A car can adopt the most appropriate GM in any given situation by hypothesis K2. Therefore, passengers and pedestrians intuitively understand what the car is doing, for what reason, and what it will do next. Thus, they do not see the AV as a brainless, heartless machine but as something predictable and trustworthy, as is currently experienced with human drivers. Visit slide, obstacle avoidance and following, 1, in MM2 line. Concept chart of MathMind. The concept chart on the next slide describes the relationships of essential elements in MathMind technology. A unit represented by a box in the chart is theory, method, algorithm, motion, merit, or some other component. The upper half of the chart is for merits. The bottom is a set of mathematical theories, the rock-solid foundation of MathMind. All merits are placed on the top half part of the chart. Merits are colored blue. The left half is a collection of capacities of conventional vehicles. The right half is a collection of capacities of future vehicles. Conventional vehicles cannot embody Omega-Mode motion or create man-made motion. An arrow does not mean a control flow. X right pointing arrow Y may mean X produces Y. A number n at the upper left corner of a box identifies a lecture number, n. Background: the autonomous vehicles are stalled. On October 6, 2022, Bloomberg published an article, "Even after $100 billion, self-driving cars are going nowhere." Earlier this year, Cruise LLC recalled all of its self-driving vehicles after one car's inability to turn left contributed to a crash in San Francisco that injured 2 people. While the industry's biggest names continue to project optimism, the emerging consensus is that the world of robo-taxis isn't just around the next left turn, that we might have to wait decades longer, or an eternity. Further, on October 27, 2022, TechCrunch published an article entitled, "It's time to admit self-driving cars aren't going to happen. I mean, self-driving isn't going to be a thing in our lifetimes and with any kind of omnipresent scale. Truly autonomous vehicles just aren't going to happen." A solution: MotionLab answers to the industry's problems. MotionLab answers with these 2 ideas as a solution to the previous problems, formalizing the motion creation capacity as sensor-independent and vehicle hardware-independent capacity. The use of the 4 concrete mathematical theories. We followed deductive approaches to solve existing problems. For instance, MathMind solved the left-turning problem as a part of the Park GM. MotionLab's mission. Our mission is to make every AVs the safest through the MathMind technology. We are ready to license for firms who wish to develop the safest and best MM vehicles. MotionLab is a self-funded independent firm. The CEO personally holds all of its intellectual properties including Eclipse-based vehicle motion simulator MathMind, the 4 unpublished mathematical theories, a PDF textbook autonomous vehicle science, and all intellectual properties mentioned in this and other lectures. Making history of mathematical autonomous vehicles. Our MotionLab possesses 4 mathematical theories that discovered, invented geometric motions, GMs, for autonomous vehicles, AVs. GMs are independent of vehicle hardware and sensors, and immediately solved numerous hard problems. Based on the mathematical theories and GMs, we can create AVs that understand mathematics and demonstrate performance surpassing human drivers. AVs need investments in deductive approaches for steady and robust advancements. That has never happened in the AV industry to date. We will make history of mathematical autonomous vehicles. Patents assigned to the CEO. US 6134486. Robot and method of control for an autonomous vehicle to track a path consisting of directed straight lines and circles with positional feedback and continuous curvature. US 8068935. Human-guided mapping method for mobile robot. W02013105957A1. Sensor-based vehicle control method. US 6314341. Method of recording trajectory data and sensor data for a manually driven vehicle. In 1976, Professor Kaneyama started mobile robotics research and development. He planned to apply his research results to self-driving vehicles in the future. His main interests were in the mathematical aspects of creating vehicle motion. Dr. Kaneyama's first significant autonomous vehicle was YAMA-BCO 11 in the 1980s and 1990s. Some of its motions are demonstrated on our vintage YouTube channel. Professor Kaneyama built the sonar-based and 68,040-based autonomous vehicle SWAN as a test bed for his mathematical theories in the 1990s and 2000s. The SWAN vehicle successfully installed direction-tracking, line-tracking, circle-tracking, park, and curvature-defined geometric motions, and more. The YouTube channel published dozens of those motion sensing capacities. Assisting Yutaka Kaneyama with MotionLab projects is Daniel Kaneyama, Director of IT Operations at MotionLab. Daniel is Yutaka's grandson, and son of Yuki Harding, Yutaka's daughter. Daniel has extensive experience in the realms of content creation, digital marketing, and e-commerce store management. Much of this experience stems from his childhood, including being featured in some of MotionLab's earliest video motion recordings with the Swan robot nearly 20 years ago. These videos, also featuring Yuki and Andrew Harding, will be shown and analyzed within the upcoming videos in this series. The following lecture series, and the MotionLab.info informational website, has been a joint production from Yutaka Kaneyama and Daniel Kaneyama. How can it be that mathematics, being, after all, a product of human thought independent of experience, is so admirably adapted to the objects of reality? Albert Einstein, 1920. We deliver the best motion creation capacity for self-driving cars. MotionLab possesses sensor-independent and vehicle hardware-independent motion creation technology for self-driving cars. If your company is interested in our licensing offer of the MathMind technology, please visit our site motionlab.info with DreamCar as the password and click the Contact button.